So again, I gotta look at the grade 9 curriculum again, but I'm not sure how much you dealt with rational exponents. So like 5 to the 1/2. Did you do that last year? No. So this is new, okay? And that's good, because everyone's on the same page. It's always good to be on the same page. You don't want to be the only one in the class, or like, oh yeah, we did this so much last year. This is easy. And you're like, what? I've never seen this before. So everyone's going to be like, what? I've never seen this before. And that's good when you've all never seen it before. Now, there is a very fundamental skill that you need to have. When you're dealing with fractional exponents, well, if I could just go to the top of the page here, we have some nice blank. If you have 2 to the 3 times 2 to the 6, you're putting up your hand. What is thy answer? Yes? 2 to the 9. What's the rule when you multiply powers? You add the exponents. Now what if I had 4 to the 1/2 times 4 to the 3 over 2? Should we do the same thing? Should we add the exponents? Yes. Okay. Now, what's going to come into play is common denominators. So, this one's really nice. Actually, let's make this, I'm going to make this like 3 over 4. That was way too nice. I'm a math teacher, I'm not supposed to be nice. So, if I have 1/2 plus 3/4, now I need to find a common denominator. So that would be like doing 4 to the 2/4 times 4 to the 3/4, which would equal 4 to the 5/4. Okay? So that's why we are going to be looking at this skill of adding fractions, because when we are dealing with fractional or rational exponents, we're going to be adding them. Okay? So 4/5 plus 2/5, easy, 6/5. 2/3 plus 1. Now, 1 can be written as a fraction anytime. Now you think, yeah, it could be 1 over 1. Yes, it could be. But we should make it a common denominator. So we will make it 3 over 3. And that is 5 over 3. What do you notice we are not adding? The bottoms, the denominators. Good. Okay? Now the other way. 2/7 minus 3/21. So I want to make this over 21. Or I could make the other one over 7, couldn't I? You could make this 1 over 7. Or you could have made the other one 6 over 21. You would still get the same answer. So now if we have that, 2 minus 1 is 1/7. Okay? You know, just about in everything you do, addition, subtraction, then you do multiplication, division. It is easier to do multiplication, division of fractions than it is addition, subtraction, because these are so nice. You just have to go 6 times 4 is 24. You go 5 times 3 is 15. So you multiply the numerators, you multiply the denominators, and then you reduce. Is there anything that can go into both of them? 3. So 24 divided by 3 is 8 over 5. Okay. This one, 4. Oh, that one's scary. That's not fraction form. Oh, that's better. 3 times 4 is 12 over 2, which equals 6. The other one is 8 over 25, which reduces to 8 over 25. Okay, now we're going to start just building this chart here, because Anybody, let's just go down the chart. What would 36 to the 1/2 equal? Okay. Well, luckily you have this awesome thing. And you can just go 36. You should always do this in brackets if you can. To the exponent, bracket, 1/2. So whenever you have a rational or fractional exponent, put it in brackets, and you get the answer, 6. What do you think 49 to the 1/2 would be? What do you think the square root of 49 would be? What do you think x to the 1/2 equals? Square root, okay? X to the 1/2 is the same thing as square root x. Now, here's a little kind of thing to make this easier. There is an invisible 2 there, right? Because what do you think 8 to the 1/3 is? To the 1/3. 2. So what do you think cube root of 8 would be? So are you seeing the common? No, it's x to the 2/3. X to the 2/3. Now maybe we could try this. Let's do this with 8. What's 8 squared? What is the cube root of 8? Or 64. 4. So the answer to this is 4. Now what is x to the 2/3? Or sorry, 8 to the 2/3? You also get 4. 8 to the 2/3 equals 4. Now, this you should be able to establish a rule from. You see where the 3 and the 2, or I should say the 2 and the 3 are in the fraction. Do you see where they move to when you put it in the other form? Now, those two are identical forms. 2/3 is nicer to work with when you get into bigger numbers. And easier to solve for x. So, what are we going to say about this? Well, let's summarize it. X to the 1/2 is the same thing as square root x. And you know what? Let's put an invisible 2 here. And let's put a 1 there. Okay, now x to the 1/3 was cube root of x to the 1. X to the 2/3 would be cube root of squared. Okay, now x to the a over b will equal what? The bth root of x to the a, or, and this will work out for you in certain situations, b of x all to the a. Sometimes it's easier, and let's use the example 8 to the 2/3. So this is the same thing if cube root of 8 squared. So that's the cube root of 64, which is 4. But what if we did the cube root of 8 squared? What's the cube root of 8? 2 squared, which equals 4. So sometimes it's easier to cube root it, I should say, and then square it. You'll actually be working with smaller numbers. Sometimes it may be easier to square it first and then cube it. They will both work. They will always both work. Okay? Now, I need us to focus on this thing right here, because I've been working with students working with this for a long time in grade 11 and 12. They get the A and the B mixed up, where to put them in the thing. How are we going to make sure we don't? I always like to see what classes can come up with instead of my way. Yeah? Ah, okay, very good. 1 divided by 2. Yeah, so if you had 1 divided by 2, oops, that's the same thing as 1 divided by 2. That's what you're saying? Okay. Is that all you want? B-O-T-I? Bow tie? Bottom outside? Top inside? That's pretty nice. Where'd you get that little one from? Oh, so yeah, you took it from that related to. That's good. Bow tie. I like it. Okay. Bottom and the outside, top and the inside. That's pretty sweet. I think you just upped our class average by 10%, just that one. Now, there is one that I have heard. So this, if you looked at this like a flower, this would be the root, and this would be like the flower. Yeah, so flower rhymes with power, right? Think of a flower. Okay, and then you got your ground, and then you got your roots, okay? And the flower is usually above the roots. If it's not, your flower's probably not looking very good these days. So the flower is the power, right? The root is the root. Okay? So the flower is the power, the root is the root. Not too creative on the root part, but you get it, right? But I like bow tie. I do like that one. I will steal it and make up my own. Okay. Let's do some examples. Give a power with a decimal exponent that can be converted to a fraction and then to a radical. So what if we did the example of 1.2? Now, can everybody put in their calculator 1.2 math, enter, enter. 1.2 math, enter, enter. 6/5. So math, enter, enter changes anything to a fraction, but always an improper fraction. Or sorry, an improper fraction, so you'd have to convert to mix yourself. And if the decimal's going on forever in like a weird, it won't convert it, right? So it would have to be an obvious terminating decimal. So then this is 2 to the 6/5, which would be 2. And if I put this What's outside? What's going outside? The root is going outside, and the power flowers the power. Or bottom outside, top inside. Ooh, Taibo. I'm making it. That's my Taibo. They'll never know where it came from. Top inside, bottom outside. Nice. Yeah. Bow tie. What a dumb one. Now that. Taibo, yeah. That rocks. Okay. Now this. Okay, are we back? We're taping here, right? So I got to get going here. If the radicand is a number, you can evaluate the power with a fractional or decimal exponent. Okay, you can. So basically, this is just saying if you had 27 to the 4/3. Now, many of you at this point will not go 27 to 4/3. Oh yeah, that's 2.846. Okay, probably not at that stage. But if you converted it to the other, where we go 27, we do this, top inside, bottom outside. Now you have two options. So you can take 27 to the 4th and then cube root it. Probably not going to be doing that in your head, but you could cube root 27. So you could just do this. Okay, what is the cube root of 27? 3 to the 4. It's the same thing as 3 to the 4, which is 81. What's up, Caleb?
Does the brackets work for like
It works for everything. Yeah, it works for everything. Okay, so let's just do some. See if we can do these without our calculators. It's so hard. They're just sitting there screaming, "Use me, use me!" But you got to use that thing between your ears. If you don't know what I'm talking about, this probably is going to be difficult. Okay, so again, put your 27. Okay, and then draw the house, and then you got to put the numbers. Tie, bow. See, bow tie looks good left to right, so I get it, but tie bow is just cooler. Cube root of 27. 3 squared. So you don't need no stinking calculators. Okay, -8. Put the house to 1/3. Bow outside. 1 inside. So cube root -8. -2. Okay. Now 25 over 4 to the exponent 1/2. So then you will go like this. Now, again, fractions take that to another level of, intimidation. But all you do is you do the top and you do the bottom. So that this is the same thing as, if you really wanted to write it like this, root 25 over root 4. Now you can split it up like that. What's root 25? Over 2. 5/2. So obviously the goal of this is for you to be able to do them without calculators. Okay, to the 3/4. So 81, draw the house. Bottom outside. Top inside. I'll go back and forth. I bow tie once in a while. Now, what's the 4th root of 81? See, I'm going to choose to do it like this. Because the cube, to take 81 and cube it, that's a big ugly number that I can't do in my head. Well, I guess that one's, that's hard. Okay, 4th root of 81. 3 cubed, 27. Okay, 16 to the 3 over 4. Draw the house. 16's going in. Bow tie. Okay. That is the fourth root of 16. 2 cubed, 8. Okay, almost done. Okay, let's not talk, let's just turn our page. Now, these ones are obviously a different level because they are using variables. So, we want to be able to just apply our rules though, and it says just eliminate the radicals. It doesn't ask me to solve them. So, this would be x to the, what would be the fraction? 2/4. Okay, which would be x to the 1/2. Okay, now 6 is one of those that after you see it, you're going to be like, okay, I get it now. But most people would have a lot of trouble with this one. So this is why having radicals turning to fractions is really nice. Because this would be the same thing as x to the 8, y to the 12, all to the 1/2. Okay, now this is 8 over 1 and this is 12 over 1. You can multiply power to powers. Okay, so if you had x to the 2 all to the 3, that equals x to the 6. If you had x to the 4 to the 1/2, it would be x to the 2. So this will give me x to the 4, y to the 6. And when there's 2 or 3, now that's all one term. They're just multiplied together. You can do that. You can't do that if there's a plus or minus sign in between. What is the fourth root of x to the 4th? Yes. So the first one is x, and root x to the 5. That would be x to the 5 over 2. That one's tricky because people forget. Oh yeah, that's right. There was a 2 there. Okay? That's a good quiz question right there. Love it. Now, this is a 1 here. So this is kind of going to where I started. What do you do when you multiply powers together? You add the exponents. So this is going to be 1, or we could write it as one thing, x to the 1 plus 5 over 2. So when you bring the x's together, so this is the same thing as x to the 2 over 2 plus 5 over 2, which is x to the 7 over 2. Okay, 8's not so bad. That's just xy to the 1/2. Or x to the 1/2, y to the 1/2. And 9 would be, now think about it before you say it, would be b to the check it table. And you're like, oh, it's not in the inside, but remember, it can go here or here. It doesn't matter. It's very versatile. Okay, you're good to go.